This is the first lesson of topic 10. In this lesson, we're going to be able to prove triangles are congruent and then draw conclusions from those in order to solve some practical problems. Then we're going to learn how to indirectly measure a distance by applying what's called cpctc. So this little abbreviation is something that is used a lot in our congruent triangle proofs and things that we've got coming up, and so we'll learn what that phrase means today, and you will hear it a lot. So remember, congruence can help us solve problems in everyday life. So when we know that two triangles are congruent, we can often find unknown measurements as a result. So we know that if two triangles are congruent, there is a sequence of rigid transformations. Those are the reflections, rotations, and translations that would map one triangle onto another. And we looked at that in depth in lesson 9.1. Also in topic 9, we learned shortcuts for proving triangles are congruent. So no longer do we have to show all 6 congruent parts. We have shortcuts that allow us to only know 3 pieces of information and still show the triangles are congruent. Those shortcuts are SAS, SSS, SAA, and ASA. We do have a 5th shortcut, HL, but remember that only applies to right triangles. So we're going to be using congruent triangles as a tool in this topic. It's not the end result, it's part of the process in order to prove something else to be congruent. So let's look at this first animation on how a park ranger uses congruent triangles to determine the distance across a pond. So in this animation, it says Anna is a land surveyor. Land surveying involves finding the 3-dimensional position of points in a landscape and the distances and angles that are between them. So Anna's been asked to consult with a local park ranger and to create a map. She needs to determine the distance across the pond. Now, obviously, she could either swim or get in a boat and find that distance across the pond directly. But what we're looking at is indirect measurement, how to find the distance across without directly measuring it yourself. So here's an overhead view of the area, and this is the distance we're trying to find, the distance across the pond. So what Anna does is she starts at one end of the pond and walks out 40 feet. Marks a point and walks out another 40 feet. So she knows for sure that these 2 parts are congruent because she measured them on the ground itself. She does the same thing from the other end, but to get to the point she made here, it only took her 30 feet. And so she walked out 30 more feet here. And so we're going to see how creating this figure here will allow her to know the distance across the pond without actually getting in a boat or getting wet. So how do these triangles help her find the distance across the pond? Well, since we knew this segment was 30 feet and this segment was 30 feet, they're congruent. And since these segments were both 40 feet, they are congruent. We have a third pair of congruencies we know because vertical angles are always congruent. So angle ABC and angle DBE are congruent because they're vertical angles. So now that we know these 3 pieces of information for each one of these triangles, we can conclude that these 2 triangles are congruent to each other using one of our shortcuts. This one is 2 sides and the included angle. So that shortcut is SAS. So now that I know this triangle is congruent to this triangle, then we know all 6 parts of those congruent triangles are congruent to each other. So I would know this side I'm trying to find, the distance across the pond, which is segment ED, would have to be congruent to this segment AC. And since AC is on the ground, we can simply measure it directly here to get the indirect measurement across the pond. What did I miss in that animation here? Oh, so she measures AC and finds it to be 34 feet, which means the distance across the pond is also 34 feet. So that helps you answer question 1 in your notes. So let's look at that. So it says, in order to find the distance across a pond, a surveyor helps a park ranger measure the following distances to create 2 triangles. How can the park ranger be sure that the 2 triangles are congruent? Since the vertical angles are congruent, mark those in your figure. we know that these two triangles are congruent by SAS. Okay. Number 2 in your notes is coming in just a moment. So what we're thinking about today is how we can use our geometric relationships to help us indirectly measure distance. So hopefully you understand indirectly means you're not directly measuring it. Like she did not directly measure the distance across the pond. She measured something on the ground that was congruent to it. So here comes our mysterious abbreviation, cpctc. So if you'll remember our definition of congruent triangles back in topic 9, it said that two triangles are congruent if and only if each of the angles and sides of one triangle are congruent to their corresponding parts in the second triangle. And remember that's 6 parts, 3 congruent side pairs, 3 congruent angle pairs. So in this course and in many mathematics courses, you will see this acronym cpctc. And this is what it stands for, and this is what you're writing in number 2. It simply means corresponding parts of congruent triangles are congruent. So that is what you are writing on number 2. Corresponding, that's your first C. Parts, that's the P. Of, we don't have O in the abbreviation obviously. Corresponding, that is the second C. Oops, I'm sorry, that's not corresponding. Congruent, my apologies. So corresponding parts of congruent, that's your second C. Triangles, that's the T, are congruent. That's the last C. Corresponding parts of congruent triangles are congruent. cpctc. We will use this a lot in topic 10 and later in the course as well. So we're going to look at a different situation than the park ranger. We were able to use congruent triangles in the park ranger situation, and we're going to use it again, but this one's a little more complicated of an example. So this one uses Bud and Travis, who love to ride dirt bikes. And so this, you may seem like, okay, this is a little far-fetched. I'm not sure they would really do this, but let's just assume that Bud and Travis are math lovers, and so they are going to use it in this situation. So it says for their spring break from college, they take an off-road trip on their bikes in the Mexican desert along the Sea of Cortez. One afternoon, they come to a deep ravine that they need to cross, and Bud and Travis know that with a good running start to build up their speed, they can jump the ravine on their bikes if it is no more than 25 feet across. So if it's 25 feet or less, they know they can jump it. If not, they need to find a different route. So we want to know, can they make it in this situation? So this is, of course, another situation where we need to indirectly make a measurement. They're obviously not going to be able to measure the distance across the ravine directly. So here are Bud and Travis, and they become symbolically these little blue and red sticks that we see here. So here is Bud. He goes to an Ocotillo cactus. Ocotillo cactus. Never heard of this before in my life, but I looked it up, and apparently, unlike other cacti, it is basically looks like sticks that are sticking out of the ground. So this is a really stiff stick that he's using as a pole here. So he goes and gets a branch off of that and sticks it in the ground 8 feet away from the ravine. So the next thing that Travis does is this is his symbolically his eye level here at the top of the stick. He is looking at the top of the pole, and he steps back until that eyesight that hits the top of the pole follows to the far edge of the ravine. So this is his eyesight. It is hitting the top of the pole and the far edge of the ravine. Okay, so the next thing he is going to do, this is an aerial view or overhead view, he can measure this distance he is from the pole. So here's the distance across the ravine. Remember, he stuck the cactus branch 8 feet away from the ravine. and he is standing so that his eyesight hits the top of the pole and follows to the edge of the ravine on the opposite side. So he is going to measure his distance to the pole, and then he's going to go off this direction that same number of feet. So he was standing 25 feet away, so he walks in a perpendicular fashion to that 25 feet off here on the ground. So remember, his goal is to be able to measure on the ground since he can't measure directly across the ravine. So now Travis is going to get involved in this math process. Travis is going to walk away from the pole until that same eyesight distance is included here. So now Bud is still looking at the top of that cactus branch until Travis's feet are at the end of his eyesight. So theoretically, the distance from Bud to Travis is the same as when Bud was standing here to the opposite side of the ravine. So now this is a distance they can measure because this is on the ground. And so they measure how far Travis is from the pole. It's 28 feet. But remember, that does not mean that the distance across the ravine is 28 feet. Remember, the pole was 8 feet away from the ravine, so they have to subtract that from the 28 in order to know the distance across the ravine is 20 feet. So can they make it? Yes, that's less than 25 feet across, so they can jump it. Here's another view of the method that they used, and so you can see that they are actually using triangles as a result of this demonstration. So remember, this is the original location of Bud when he stepped off so that he could see the top of the cactus branch and the edge of the ravine. And then this is his second time to be that same distance away, so they used the prime symbols here, and his distance to the bottom of Travis's feet here. Okay, so how would we know that these two triangles are actually congruent to each other? Triangle BUD, the original one, and triangle B prime U prime R, which is the second one. So that's what we're going to be looking at here in question 3 on your notes. So let's look at question 3 actually on the notes. This kind of helps us see a little bit that we have two different triangles here. It says in the box at the left, draw triangle CEA. So you're just drawing this triangle here. So I'm going to measure or draw CEA here. Here's CEA, and I'm just sketching it, and you can do that as well. And in the box to the right, we're drawing CDB. So here's CDB. It goes the opposite direction, like this. CDB. So a lot of times when you have overlapping triangles, like we do with the motorcycle demonstration, it's better if you kind of look at the triangles separately instead of trying to read them when they're overlapping like they are here. So that's why it's kind of suggesting that we do that. So if we look here, we have taken these overlapping triangles and drawn them separately here. So let's look at these two separate triangles. What information would we know stayed the same in these two triangles? What are informations that we knew? Well, remember the BU right here on this segment, that represents Bud. And did his height change when he walked from here over to here? Of course not. So we would know that BU and B prime U prime would be congruent to each other because that's still Bud. The other thing that we know didn't change is if he's standing up straight, remember we've talked about this many times, that's your height, but you always have to be what relationship to the ground for that truly to be your height. You have to be perpendicular. So we would know angle U here is a right angle, and of course U prime would also be a right angle because that's still Bud standing there. The other distances we know for sure are the same. Remember, we are finding the length across from U to D, but we were able to measure U prime R. And we know those distances are the same because of the line of sight that he used. So we could use SAS as our shortcut. The other thing we knew was the same is, remember his eyesight level? He was looking from B to D across the ravine, and he did that same distance when he was looking at Travis's feet, which is B prime R. So we would know these two would be the same. So we could use HL because that's the hypotenuse of the right triangle, and of course his height is the leg. So HL would be a good shortcut here. All right, we will finish this in the next video.